So let's try and understand what Kepler's laws say. So there are three laws that he had given as we discussed. First said all planets move in elliptical orbits with sun situated at one of the foci of the ellipse. What's the meaning of this sentence? So if you look at this particular picture, what you see here is an ellipse. This is a geometrical shape. Now in this ellipse there are two things that we have, one which is called as a minor axis and one which is called as a major axis, and then there is one point which is called as the focus. So when he defined the first law, what he was saying is that when the planets revolve around the sun, they revolve around the sun in an elliptical orbit with sun situated at one of the foci. Why one of the foci? Because there are two focus here. So one on this side and one on that side, right? So if you consider this as the planet, either this is the sun or this is the sun. So this is the placement of the sun that will be observed with respect to the motion of the planets. This is the first law that he had given. Now, when you talk about ellipse, ellipse as a shape is a shape which can also convert to a circle. How exactly? If you look at this, here currently you have two axes, one which is called as minor axis, as you can see visibly, it is smaller, and then the second one which is bigger is called as the major axis. So when we talk about the major and the minor axis, these are the two which are different in length, and that's why you get an ellipse. Take an example where minor axis and major axis are same, they are equal to one another, then in that case you get a circle. So circle in a way you can say is a special case of an ellipse, right? So that's why even when you say circular orbit is nothing but a special case of an elliptical orbit. So this is what the first law says, that planets revolve around the sun in an elliptical orbit with sun situated at one of the foci. Then what's the second law? Second law says planets sweep out equal areas in equal time. Okay, equal areas in equal time. Just remember this area. We are not talking about the length. We are talking about the area. So this law comes from the observations that planets appear to move slower when they are farther from the sun than when they are nearer. Let's look at this law. So if you look at this particular picture, what you observe is there are two cases. One, when we are looking at time equal to 0 to 10 days on the nearer side, and then when you are looking at time from 0 to 10 days on the farther side. So a planet starts from here and goes up to here. It takes 10 days of time, and the same planet, while it goes to the other side, going from here to here, it takes 10 days of time. So what we observe is, if you are observing it from the sun, then what you see is that while the planet is nearer to the sun, in that case it appears to be moving faster, because equal areas in equal intervals of time. The time interval here also is 10 days and here also it is 10 days. So in equal intervals of time, equal areas. How do we get the areas? We get the area like this. We get the area like this. So if you talk about the first shaded area as compared to the second shaded area, what's happening? These two lengths are getting longer, and since these two lengths are getting longer, this length is getting shorter, because area has to be kept the same, right? So something which goes back to your class 8th and 9th mathematics, that when you have areas, there are two triangles that we are taking here. If the length of two of the sides of the triangles are increasing, then the third side has to decrease. So that's why here these two sides were shorter, so that's why this side was longer. Here these two sides are longer, that's why this side is shorter. Simple mathematics, and this is something that was observed for all the planets as well, and this became the second law, equal areas in equal intervals of time. So this is the second law. So the objects will move faster when they are closer to the central object. It moves slower when it is farther away from the central object. This is in case of the planets, and this is something that was generalized by Newton, that something similar will happen for any two object system where you have something as a central object and you have another object which is revolving around that particular object. So this is the second law. Then we have the third law. What does the third law say? The time it takes for a planet to complete its orbit depends on the size of the orbit. Pretty simple. If you just observe the words, it's not something which is out of the ordinary, right? Time it takes for a planet to complete its orbit depends on the size of the orbit. Meaning what? What Kepler said, the orbital period squared is proportional to the size of the semi-major axis cube. P square is equal to A cube. This is what he had said. P in years and A being taken in astronomical units. We already discussed what is astronomical units, right? So T square is equal to A cube. Pretty simple. We are saying that if the size of semi-major axis is increasing, meaning if the length of the path increases, then the time that is taking to go through that part will also increase. Again, very simple, right? Coming from very simple logic, that if you increase the path, you will take longer amount of time. This is what this law is saying, that if you have to cover a longer distance, you will take longer amount of time, given that the speed remains the same. So something similar is happening here as well. Basic physics is something that we are talking about. So then again, in this case also, Newton generalized the things. He said that something which is happening only between the earth and the sun, or planets and the sun, can be generalized to other systems as well, and it also depends on the mass. So he also brought mass into the discussion, not important for the examination. So there are three laws. In simple terms, what you need to remember are, there are three laws that were given by Kepler. What first law says, what second law says, and what third law says. That's it. Just be sure that you know these three. Nothing beyond that is required for the examination at all. Now the next topic that we have to see are types of orbits. Now there are many terms that might be thrown to you. If you look at the newspapers, if you have been going through the newspapers, you'll observe there are many kinds of terms that come into the picture. For example, you have low Earth orbit, medium Earth orbit, and high Earth orbit here. But apart from that, there are other terms as well. For example, you might have come across the term of sun synchronous orbit. Then you also have geostationary orbit, something which is called as geostationary orbit. Then you have something which is called as geosynchronous orbit. Then there is semi-synchronous orbit. So there are a lot of terms. You might have come across the term which is called as Lagrange points. Then you also have the geosynchronous transfer orbit. You also have something which is called as Hoffman orbit. So there are many terms, but all these terms that we have on the screen right now, all these terms can be classified into these three. And if you understand these three, then all these other terms become very simple for you to understand. So let's try and understand what these three terms mean. And these are the major types of orbits. You have the low Earth orbit, you have the medium Earth orbit, and you have the high Earth orbit. Now what do we mean by all these terms? Let's try to understand this one by one. First of all, look at this particular picture. What do you observe here? That there are three different orbits here, correct? One which is very near, this is called as the low Earth orbit. There is another one which is little farther away, which is called as the medium Earth orbit. And then there's the third one which is farther away. This is called as the high Earth orbit. Observe one difference in the motion. What's the difference here? When you look at the low Earth orbit, what do you see? You see that the object which is moving in the low Earth orbit is moving very fast, correct? The object which is in the medium Earth orbit is little slower, and the object which is in the high Earth orbit is even slower than the mid Earth orbit, right? So go back and recall second law, equal areas in equal intervals of time. What is the statement that was made there? The statement was, if you are near to the central object, you will move faster. If you are away from the central object, you will move slower, right? Something similar can be observed here as well. Something similar can be observed for every satellite also that we launch. So when we come to the satellites, we'll discuss about this, that the time period of revolution of a satellite which is near to the Earth is much faster as compared to the satellite which is much farther away from the Earth. So something similar will be observed there as well. So these are the three types of orbits. Now let's try and understand each of these types of orbits that we have and what is the meaning of all these orbits. So first of all, to understand all these orbits, what we need is to understand all the factors that determine the orbit. So the first factor that we have understood is the height, right? You have the medium Earth orbit, you have the high Earth orbit, you have the low Earth orbit. So these are coming from the first factor, that is height. For example, now height will be dependent on what kind of application we have. For example, let's say you want to take pictures of the Earth. You need to do weather monitoring. You need to observe the Earth. You need to do the surveillance of the Indian borders. You would need a satellite which can take clear pictures. You would need a satellite that can observe the Earth properly in high definition. Can you do it from a satellite which is very far away from the Earth? You cannot. So you need to keep this kind of a satellite near to the Earth. So that's why these kind of satellites, which are called as Earth observation satellites or remote sensing satellites, they will be kept near to the Earth. So height becomes a very big factor depending on the application, right? So depending on the application, we have the height as one of the factors. Then the second factor is eccentricity. Now when we talk about the ellipse, we discussed about an ellipse, we saw the shape of an ellipse. In that particular shape, what happens is there is one value, that is E, or which is called as eccentricity. This determines the shape of the orbit. So the second factor that we are looking at is basically the shape of the orbit. First was the size of the orbit, second is the shape of the orbit. So eccentricity value basically is between 0 to 1. It can be greater than or equal to 0, and it will always be less than 1. It will never be 1. Please remember this. It can be 0.9999, etc., but it cannot be 1. Now, what is the meaning of this value E? When you talk about the value of eccentricity for E, this basically means what? When the value of E is equal to 0, it means that the length of major axis is equal to the length of minor axis. So if the length of major axis and minor axis are same, it simply means what? It simply means that it is a circle, because all the axes have become the same. Now it is the diameter, it's not an axis anymore. When the length of semi-major axis is much greater than the length of semi-minor axis, in that case the value of E is approaching towards 1. So this value will be almost approaching 1, maybe 0 0.9, 0 0.95, 0 0.99, but what will happen is that it will be a highly eccentric orbit like this. So value of E equal to 0 would mean that it becomes a circle. It becomes a circle like this, that the length of major and the minor axis become the same. But when you look at the value of E is equal to 0 0.9, it means that now this is the focus, and this is the length of semi-major axis, and this is the length of semi-minor axis. So things change like this. So this will determine the shape of the orbit. So first important factor is what? First important factor is height of the orbit. Second important factor is the shape of the orbit or eccentricity. Third important factor is inclination. Now, inclination also becomes a major factor because it determines how you want to use the satellite. So many times you will see that the inclination with respect to the equator is 0 degrees. Why 0 degrees? Because we need to observe the Earth from the equatorial plane. Normally when you have the communication satellites, most of the communication satellites need to do this. And that's why communication satellites will be placed in the equatorial plane with no inclination. But when you have remote sensing satellites or Earth observation satellites, we need to put them in the polar orbit. Polar orbit meaning that they will be highly inclined. They will be highly inclined, just like the poles of the Earth. Similarly, you will see that they will also be inclined towards the poles of the Earth. So that's why this again becomes a major factor depending on what application you have for the satellite. So that's why these three are the major factors that determine the kind of orbit that you have, determines the kind of an application that you have. So any satellite that is being launched will always depend on these kind of factors. Even if you don't remember all the things that we discussed here, what you need to remember is what are the factors. Why these factors, even if you don't remember in the exam hall, will not matter. But what factors are there, it will matter a lot, because it will make your questions simpler. We'll look at some of the example questions towards the end. You will understand that if you have understood these concepts, even if you don't know the direct facts about these satellites, you will be able to answer the question without even knowing the facts, without even going to the facts and mugging of that particular law.